Okay, I think we can start this training demo site seminar. So the objective of this seminar is to present the demonstrations, the two demonstrations of the SCORS technology. The objective is to demonstrate the integrated hybrid system for store energy in different conditions, and also the different components of this integrated system. So the first presentation will be made by the coordinator of the SCORS project, Erwin Gilling from TNO. I don't know, Erwin, are you ready to present?
Yes, I am.
Okay, thanks.
Almost ready to present. I will share my screen. Thank you, Louis. Okay. Okay, all right. So thank you for the introduction, Louis. I will give a short introduction of the SCORS project, its objectives, and the technologies that we developed towards the demo sites that we implemented them on. So what is going on? We are in the middle of the energy transition. We generate a lot of electricity with wind, with solar, but sometimes the demand, for example, for heating, cooling, taking a shower, cooking, is not exactly in line with the generation, because during the daytime we have sun, and maybe in the evening we want to use this energy. So what's the solution? That could be to store the energy locally in the urban environment, so in houses, in apartment buildings. Another issue is that in a lot of countries, and especially in the Netherlands, we have a problem with the local power grids. We cannot deliver all the power that we generate ourselves from solar and wind to the local communities, because we don't have enough capacity on the grid. So in the summer we have a lot of peaks on the generation side, and in the winter on the consumption side. And here you see a little map of the Netherlands, and all the red areas are just full. You cannot add additional PV panels or wind turbine energy there anymore. So there's a limited possibility for installation of large-scale parks, and also there you could think of locally store the energy, and that's where SCORS is all about. So SCORS is about self-consumption of renewable energy by hybrid storage systems. And self-consumption means that we want to use as much energy as possible that we generate ourselves in the urban environment locally. So the SCORS project combines and optimizes multiple energy generation equipment, storage, and consumption at a local renewable energy, electricity, and heat grid supply. The SCORS project has 12 partners and started in 2017, and it's ending this month. So what's it all about? We have a surplus of energy, of locally produced electricity, and we could have also district heating as inputs in our houses, in our buildings. So what can we do? We could store electricity, we could convert it to heat, and we could also store heat. So this is a hybrid solution to intermittency of the energy. And then, of course, we use the energy for space heating, for domestic hot water, electricity use, and we could also refeed it back towards the electricity grid in case that would be possible with respect to capacity. So the project aims to increase the self-consumption by introducing new sources of flexibility to the grid. This is the consortium. We have industrial partners developing equipment and new solutions for energy storage and generation. We have the demo partners and the consultancy partners for the evaluation of the demonstration. We have research partners working on the supply, energy conversion, and storage solutions. And we have partners working on the demonstration and exploitation and dissemination. So it's quite a big consortium along the whole value chain. So the objectives are to demonstrate new compact hybrid storage technologies on the local side of the grid, so increase self-consumption, and by using innovative new solutions, we're bridging the gap between supply and demand. But also regionally, we introduce more possibilities for flexibility. So because we can store locally, we increase the flexibility of the grid. And you could even say that it defers investments in the energy grid, but that was 2017. At the moment now, we are investing a lot in the upgrading the energy grids, albeit that's far, yeah, it's far too late, and we envision that there will be a need for storage systems anyway in the coming decennia. These are the technologies that we developed. So we want to reuse second life lithium-ion batteries, optimize electric-driven heating with intraday phase change material heat storage, water-to-water heat pumps combined with hybrid PV and solar, air-to-air heat pumps, and then also do optimization of long-term loss-free heat storage technology. And this is all integrated into a building energy management system. And of course, we do an assessment of all the economical potential of the whole system. So these are the two demonstration cases. We have a demonstration case on site in Austria, in Gleisdorf, and in Agen in France. In Austria, we have a connection to the heat grid. In France, we don't, because in France, most of the energy is generated by electricity and not by heat. So this is an overview of the two demo sites, and we come back to it later. These are the two locations. One in Agen is an apartment building. In Gleisdorf, there is an already existing residential building, and it's connected to both the networks. So let's go to the technologies quickly. This is how it looks like. This is the heating with the air heat pumps and the PCM storage, constructed and tested by Kampa and France Energy Laboratories. And here you see a unit that is a prototype installed in a living room or in a big bedroom. And this equipment can temporarily store energy and release it again when it's needed. This is the solar heat and water-to-water heat pump developed by Heliopac. Here you can see it on the roof. And this is a solution for the production of domestic hot water. It uses a heat pump, low temperature, with flexible solar collectors. So thermal collectors, which can be used in almost all climatic conditions. Come back to that later too. Another system that we tested is the photovoltaic thermal hybrid solar collector, the PVT, which combines both electricity generation and heat for collective domestic hot water production. So this improves the efficiency of the photovoltaic panels through the heat transfer. Essentially, it's cooled. So you take heat out of the panels too, which you can use, and the cooling gives you a better efficiency of the solar panels themselves. The demo site in Agen has a big roof where we put a PVT on, and it looks like this. So this is permanently installed there now, and it has been tested. So we're using the data of this. Then the chemical looping storage, which we call Redox Heat. This is aimed to store heat seasonally, because you can store it without any loss. And this is done by doing a chemical looping by oxidizing and reducing metals. And the reducing is done by using hydrogen, and the hydrogen is generated by green electricity. So this is also a sustainable storage system for heat. However, this system was not installed on the demo sites because it was not large enough and not developed enough to be used. So this is the system that was used and developed in the SCORS project in the lab at TNO in Delft. And then we have, for electrical storage, second life batteries. And these are refurbished battery units from electrical buses. You see them here. You see also the control cabinets here in the rooms, and this is the space. I think this is in Gleisdorf, these pictures, and we have a similar setup in Agen in the building. Second life batteries was a good idea in 2017, but the analysis and the technical results of the project are that it may be not a good idea to use second life batteries, but at this stage, where lithium-ion batteries become cheaper and cheaper, it would be better to just install a new system that will be supported by the manufacturer of the system, because we run into a lot of problems interfacing these batteries that were meant for vehicles in a stationary application. So then everything is connected by a building energy management system, and that system controls the equipment towards an optimal point based on predictions, so of the weather, and also on the demand side and the available energy and energy cost. So this connects everything together. The battery, the CLC, the heat pump, the space heating, it connects to the grid and the district heating, and it can decide what to use when and when to store what. And this is a rack with all the servers and equipment where the BEMS is running on. Then there is a spin-off which was not foreseen in the project before, but this is actually a very nice result of the project, which is a heat storage solution for buildings using very highly insulated water buffers. And yeah, this mechanical solution is patented. I'm not going to tell you how it works. And we have a spin-off company now, which was started by KMG and TNO Systems, Koenig Metal. And this vessel can keep water hot enough to take a shower for over 4 days. So if you look here, for example, a standard system from on the market will cool down very quickly, even with insulation. And this system, this buffered vessel, keeps the energy much longer than what's now in the market. And this is now already being manufactured and marketed. So that's a nice spin-off. And this can also be used very easily, replacing existing hot water buffer vessels in any building. So this is the new company Newton, a result of the SCORS project. And with that, I thank you. And this is what it was the introduction. And today we'll go into more detail of the demo sites themselves.
Thank you very much, Erwin. Is there any question to Erwin about this presentation? No? So, okay. Now we will pass.
Maybe I have one
yes.
question, please.
Yes, please, Gilles.
A question to Erwin. You talk about limitation of integrating more PV in Netherlands. Is it only focus on PV power plant, large scale or utility scale power plant, or also limitation that could be that is set to PV on buildings?
It's already a limitation for PV on buildings. Yes. Yeah. You now put in that area PV on your roof, you cannot deliver back to the local community anymore already. So it's already a limitation there. Yeah.
Okay. Thanks.
Okay. Thanks. More questions? No. So now we will pass for the second presentation. In this presentation, we will show you a video that we produced about the demo sites. So I will share now my screen. So in the web page of the SCORS project, there is a page dedicated for the training materials. So here you can find different training materials, and we developed 8 videos about the different technologies of the integrated system. And we have also one video about the demonstrations. And I will show the video.
Where partners introduce the concept, technologies and their demonstration. In this video, partners from EDF and AEE InTech will explain the demonstrations. What are the locations and buildings chosen for the demonstration and why?
In Agen, south of France, we have chosen a residential building to demonstrate the SCORS project. The residence is composed of 115 apartments. It's a typical construction for France and its compliance with the thermal regulation for buildings built after 2012. The warm oceanic climate and the internal insulation make it possible to have low energy needs for space heating. Therefore, there is no district heating connection.
The demonstrator in Gleisdorf, Austria, consists of an office building combined with 3 houses. The 2 buildings in the south are the office, and the row in the north are the 3 houses. All buildings are connected to the district heating system of the city. With this demonstrator, we can test how the SCORE system operates with a mix of office buildings and houses.
What are the SCORE system configurations being demonstrated?
The residence is equipped with multiple energy systems. For space heating, an air-to-air heat pump is used to provide both heat and cooling. For the SCORE project, some apartments were also equipped with electric heater panel with phase-changing materials for storing heat. For the domestic hot water, the building is equipped with hybrid photovoltaics and thermal solar collector. They provide heat to a water-to-water heat pump and renewable electricity to the building. The water-to-water heat pump is also connected to a hot water storage. On the electricity side, batteries support the system and reduce the need for electricity from the grid. A BEMS, Building Energy Management System, orchestrates the system, and manage the energy flow between the components.
One part of the SCORE system is located in the central boiler room of the building complex. Here, 2 heat pumps provide heat for space heating and hot water. The hot water is stored in a buffer tank. A building energy management system, which is developed in the project, controls the electricity for the heat pumps. The electricity either comes from the PV, the batteries, or the grid. This depends on electricity prices and local energy generation.
The second part of the system is outside, in 2 containers. In the left container are the electrical components, a PV on the roof, and inside are the batteries and the inverter, which connects the PV with the electricity grid. In the other container is a small hot water tank and a test version of the long-term thermal energy storage, called CLC. With this, surplus electricity from the PV can be stored as heat for a long time with very little losses, and then it can be used to heat up buildings in winter.
What are the key performance indicators being analyzed in the demonstrations?
By integrating several components, the SCORE system may represent some complexity. So first, we are analyzing the overall energy balance of the building per usage and performance of each component. For instance, actual coefficient of performance of heat pump are key figures. In the SCORE project, the main objective is also to demonstrate how we can optimally use local and renewable resources. Self-consumption and self-projection ratio are key performance indicators in that regard. SCORE system is also connected to the electrical grid. So load curve describing extraction and injection into the grid is also monitored and analyzed. In addition, environmental impact are also analyzed through carbon emission and compared to the reference scenario.
The goal of the SCORE system is to optimally use the local available renewable energy in the building. The performance of the SCORE system is measured by a number of so-called key performance indicators, short KPIs. The most important indicators are the energy consumption of the building, the renewable energy generated on site, and the share of renewables in the total energy consumption. We also look at the hours in a year where the system runs only on renewable energy.
What are the main results obtained so far?
The key components for the SCORE system in Agen are in place. The BEMS, Building Energy Management System, and the communication to the other components still need to be validated. Based on monitor variables, space heating, domestic hot water, and other usage were also evaluated. This important milestone is crucial to calibrate the simulation model. They will be used in the end to operate the demonstrator and also derive the reference case. The test period will be carried out until the end of the project, and the demonstrator result will be analyzed all along.
Here at the Austrian demonstration site in Gleisdorf, We've already installed all of the main components of the SCORS system, and each of these have been tested individually with the BEMS algorithm. We will now begin the measurement period of the project, in which we will collect and analyze data for the complete SCORS system. At the end, we will then evaluate this data and the overall performance of the demonstrator. In parallel to the demonstrator, we've also built a number of simulation models with the purpose of being able to test the BEMS algorithm in a virtual environment. The second purpose of the simulations is to then build on a number of so-called SCORS future system scenarios in which we evaluate the performance of an optimized system with the technology scaled at the lowest possible cost.
Although the SCORS system has been validated and demonstrated in these two locations, is it easy to adapt and efficiently use in other regions, namely in Europe?
The replicability of the SCORS system is a very important outcome of the project. One of the main goals was to not only demonstrate the maturity of each of these technologies, but also to be able to identify key barriers which might hinder the integration in larger systems. So far, we've observed that all of the technologies in the Austrian site could be commissioned without the need for any deep renovation in the building. However, due to the differences in maturity of these technologies, technicians in the field were not always familiar with all of these. It is therefore a conclusion of the project that more work needs to be put into fostering training such that all of these technologies can be implemented in the overall system. Our simulation models are also an effective tool to be able to evaluate the performance of SCORS systems in different building types and regions around Europe, so long as adequate consumption data and weather data is available.
SCORS gathers 12 partners from 7 European countries who are working towards the common goal. Watch the next video in the training series.
Okay, now the next presentation will be about also to present these two demo sites. So if you have questions about the video, it's better to put your questions after the next presentation. So next presentation is a presentation of the demo site A and demo site B. The presentation is divided by two parts. Keith O'Donovan from AEE InTech will present the demo site A in Austria, and Gilles Plessis from EDF will present the demo site B in France. Keith O'Donovan studied mechanical engineering at University College of Dublin, Ireland, working at AEE InTech since 2017 in Department of Cities and Networks, a specialty in modeling, simulation and integration of renewables and storage into district heating systems. And Gilles Plessis joined EDF Research and Development in 2010 to work on modeling and simulation for building envelope and energy systems. Since 2021, he leads a project on photovoltaic self-consumption for the EDF group and coordinates collaborative research projects in that domain. Please, Keith, can you start with your presentation?
Yes, good morning, everyone. Do you see the presentation? Okay,
yes.
Great. So I will start with an overview of the first demo, which was in Austria. A lot of the info you've already got an overview in the video. So this building consists of a mixed use, so it comprises of a number of offices and residential buildings in the same complex. So this is actually our research institute at INTech, where we installed and commissioned the SCORS technologies. And the key difference between this one and the building in Lejeune is that we have a low temperature district heating connection to the building. And the overall concept is that we commissioned a number of these SCORS technologies as outlined, such as the heat pump and the PV system, to act as a second source. So we see here the district heating connection, and as a second source of heat and electricity, we have our SCORS technologies. So essentially the main supply of heat for the buildings, so the office and residential, can either come from the SCORS system, and the district heating system is essentially used as a backup where we don't have sufficient heat in the SCORS buffers, which was provided by the heat pumps or the CLC system. So the technologies installed on site, as mentioned, we had a small collection of PV panels mounted on the roof of the container outside. The heat pump system from Heliopac, which we'll go into more detail later, consists of 2 heat pumps at 12 kilowatts thermal supply each, and they provide the SCORS buffer with heat at about 65 degrees Celsius, so it's sufficient for both space heating and domestic hot water usage, and it's fed to this 2,000 liter buffer. The district heating itself is then providing heat for both domestic hot water and space heating as a backup. And we also use the grid as a low temperature heat source for the evaporator side of the heat pumps. In addition, then the storage technologies, as mentioned, we have the CLC, or the redox heat system, which was briefly outlined earlier. This is so due to some the development of the CLC itself could not be scaled up to an adequate size for the demo. We had installed an emulated system, so this is based on lab data collected from TNO, such that we can deliver heat in a similar manner as the CLC itself into the SCORS buffer. And lastly, the second life batteries, which were installed, were not functioning during the monitoring period, so these were emitted in the demo itself. However, as we'll get into, the simulation side focuses on modeling the whole system, and therefore the best data we had on the batteries were then included in these future system scenarios. So that's the outline of the schematic. As we see, as mentioned, the heat pumps are connected to the SCORS buffer, and secondary inputs to the buffer were the CLC itself. So all the electrical components, as mentioned, the battery and the CLC converter cabinet is all located outside the building. And then inside the building itself, we have our main buffer and heat pump systems, which all act as another source for the buildings outside of the district heating system. So in addition to this, we have, of course, the BEMS system, which is supposed to communicate with each of these subsystems, and it tries to optimize the self-consumption of locally produced PV electricity. So in addition to this, we had looked at detailed simulations. So we took the prediction scripts from the BEMS algorithm and coupled these with simulation models of the building itself. So we collected first monitoring data on the consumption of the building and tried to characterize this in a model so that we can see the plausibility of how the BEMS behaves in a virtual system before testing it on the actual demo itself. In addition, these simulations were then used to evaluate for year-long periods the impact of individual technologies on the whole system. So namely the reduction in energy from the grids by implementing the PV system or the heat pump system alone. And then we looked at parameter sweeps, so the variation in capacity for our electrical battery system and the CLC itself. And finally, we also looked at the impact of the SCORS system for varying electricity price markets, so not just for flat tariffs, but also day-ahead pricing schemes where the BEMS can utilize the electrical battery to store electricity from the grid during the cheapest period. So to optimize not only self-consumption, but to achieve the lowest possible electricity bill for the occupants of the building. So here, for example, is a number of outputs from the model where we see this general reduction in total dependency from grid and district heating for the building through the gradual introduction of the heat pump systems, various PV areas up to a max permitted amount, and also the introduction of our storage systems. And a lot of this was in the end quite dependent on the models, as we did have a lot of technical issues with the demo, which we learned from. So as mentioned previous, the PV system itself, we had difficulties there, and also the scaling of our individual systems. We found that the building had a relatively high consumption for the amount of PV area we had. So a lot of the generated PV was often being consumed directly in the building. So therefore, you're not always getting a lot of surplus PV in which you would then send to your storage system. So this is dependent obviously on the building consumption itself, and also the availability of space to install these systems. In the end, we are limited by time for the monitoring as well. So to have a full year of data with all of the systems functioning is very nice to see and evaluate these yearly KPIs. But in the end, you are quite limited with getting adequate data for the whole year round. So this is essentially where a lot more focus was then put on simulation. So getting the most out of our monitoring data and try to recreate this as best as possible in a model, then to get yearly technical and economic performance indicators. And last point, we also use then this model to test simulated variables against monitoring data. So for small windows of monitoring data where we took collected weather data, we fed this identical weather data into the simulation models to observe the validity of individual subsystems. So comparing the COP of our heat pump systems to what was observed in the field. And also things like predictions of how space heating might look over a certain time period from the BEMS. So that's it from the Austrian demo side. Gilles can now give an overview of what was done in Agen in France. So I can pass it on, or if we have time, I don't know if we keep questions to the end of this session, Luis, or...
Yeah, I think we can pass now to Gilles, and after we have time for the questions.
Okay.
Thanks.
Do you see my screen?
Yes.
Perfect. Okay, so I will go through the description of the demo 8 case quickly, as we have already seen some overview in the video, and then focus more on some key performance indicator on the demo, and also some learnings from the simulation as for the demo 8. So basically, this is a building located in south of France. Climate, it's warm oceanic climate, so in that regard, we don't need district heating compared to the Austrian demo case, and that's also, and the space heating, sorry, is provided by electric heating mostly, and that's why also the building is highly thermosensitive compared to the electric system, sorry, regarding the electric system. Okay, so then first for the space heating, the space heating is covered, and space heating and air conditioning is supplied by an air-to-air heat pump, which is a bit aside from the SCORS system, which was not installed for the SCORS project only, but for the SCORS project, we installed several components. So PVT collector for supplying domestic hot water. So PVT collector is connected to water heat pump. 3 times 12 kilowatts of heat pump, 7,000 liter of hot water storage, and coupled with a 36 kilowatt peak of PVT, so roughly 200 square meters. Second life battery also were installed for around 64 kilowatt hours, and also some heaters, electric driven heaters with PCM, so providing storage capability in some flats, so only not everywhere in the building. And each unit is could cover the heating needs for 2 kilowatts. And basically the storage capacity is 4 kilowatt hours per unit. And then, as I mentioned also in the video, the building energy management system from Siemens is orchestrating the operation of all these components to be able to identify where we want to store energy coming from the sun, for instance, into the electrical battery or to the PCM storage, for instance. So you see some schematic at the bottom of this slide with the PVT system from Heliopac here. Oops, sorry. PVT system from Heliopac for the domestic hot water. Then you have the figure or the picture of the electric heater panel from Kampa. So it's a schematic, but it was also installed in one apartment. And the second life battery for Seapower, and the BEMS also schematic from the BEMS. So regarding some key indicator for the performance of this demo, so the energy consumption per usage was monitored from 2019 till the end, 2022. But here you see some figures of the consumption per usage between 2019 in blue and 2020 in orange. So basically, space heating was stable in these 2 years, and we observed also, thanks to the system of Heliopac, some reduction on the domestic hot water side. So we have also the schematic here of the Heliopac system, 3 heat pumps connected to several hot water storage. PVT systems are on the roof, as presented also earlier by TNO, and provide electricity to heat pump, and also are connected to the cold side of this heat pump to provide thermal energy also to the heat pump. Basically, looking also at the performances of this domestic hot water between 2020 and 2022, or end of 2021, sorry, we've been able to see how this system is performing. For instance, you at the end will be able to operate the system nicely, I would say, without having needs for backup, which are described in dark blue here. You have the needs of the of energy from the backup, and part of energy which is actually provided by heat pump in light blue. So useful energy are in red. So you see that a bit the variation. A large share of this energy is also used for the distribution loop. And you have the coefficient of performance in stars, in green stars, and basically it's around 2.5 to up to 3. As Keith mentioned also in the previous presentation, since we've been not able to demonstrate all the KPIs we wanted to do with the demo, we've been also extending the study with a simulation for other purposes also, so prospective analysis and making some sensitivity analysis also. And that was done with a design of experiments where we wanted to test several configurations, so with and without heat pump, considering the PV installed on the roof and extending also the PV capacity installed, and also varying the storage capacity, electrical battery. Other parameters were also varied. And basically, as for all this kind of sensitivity, the conclusion are of course dependent of assumption, which may have changed a lot since the beginning of the project. So you see here, you can see here the different cases, reference B with only electric heaters and boiler, and the SFSB with no PV, where we integrate only heat pump. And then we add PV and several sizes of electrical battery. So in terms of learnings for this, from this sensitivity analysis, so you have the design of experiments, which is kept here. So 3 main first case here, and then we have integrated some battery capacity variation from 50 kWh to 300 kWh. And in terms of performance, what we can see is when we are in reference B case, we have a large need for the electricity from the grid, more than 600 megawatt hours per year, and then introducing heat pump make this electricity from the grid reduce drastically, and then also the PV is also bringing some additional performance considering this supply from the grid. Thanks to the battery, we can also reduce the surplus, which is exchanged back to the grid, and that's also, as Erwin mentioned in the first presentation, some nice also feature for our country with this kind of limitation. Looking a bit more to the duration curves, you can see that in the right-hand side of the slide, we see that the heat pump bring the most of the decrease in electricity from the grid, especially at peak power, from more than 200 kilowatts to 130 kilowatts roughly. You have also some decrease of power demand from the grid brought by the PV, and also some small share by the battery, but it's much more at a low power period, let's say, so during summer or interseasonal period. So as mentioned by in the previous presentation by AEE, so we have, in terms of outlook, we had several difficulties in operating the demonstrator because the system is quite complex and the components also were not all at the same technology readiness level. We had, for instance, some issue to recover clean data for analysis. Electrical battery was also not demonstrated properly. We had some communication issue, for instance, with the BEM and EMS perturbation issue also. And PV sizing, sizing of the PV inverter and the constraint from the PVT installation brought also some issue on demo side. That's why we rely also heavily on simulation to get an overview of the potential of this kind of system. So key takeaway: share of renewable energy usage may be significantly increased with this kind of building and system, mainly the heat pump and then PV. PV sizing is also the key. Is also key in this kind of study. Larger is better, but also it should be adapted to the need and adapted to the constraints also of the building. That's what we took into account, for instance, in terms of available surface area on the roof, and electrical battery are also nowadays still quite expensive, at least for the French context, for the service they provide at the local level. That's what that was also one of the conclusions of this project, to try to find also values for this battery more on the grid side, for instance, for flexibility purposes, for instance, and not only for energy reduction at the building level. All from my part. Thank you. Thank you for your attention, and I will be pleased to answer any question if you have.
Thank you very much, Gilles, and thank you very much, Keith. Are there some questions about this presentation? So it's not easy to demonstrate all integrated system with the different subsystems, with a very strong connection between them. At the same time, it is important to have some simulations to try to see what's happened in the different conditions and with the different combinations of the system. So the demonstration have done in the south of France and in Austria. Gilles and Keith, do you think that this can represent the main regions of Europe, or for the different conditions we should to test in the different regions, in different climatic conditions? What do you think? It is enough to extrapolate the performance of the systems for the different regions of Europe?
Yeah, I think in the Austrian context, or at least when there's a district heating system present, it's very much the question of why you want to reduce the impact on the district heating grid, because there is also a lot of development in these heating systems and they're becoming cleaner as well. So to install things like heat pumps and battery systems on top of it to reduce district heating consumption, it's sometimes questionable why you do it, because there's two kind of developments going on there. So yeah, I guess for current systems where you still have a high share of carbon energy sources in the heating grid, then it makes sense to shift away from it in this way. But at least in terms of getting a hybrid energy system, and we were able to show that we can use certain interfaces from power to heat in the building, I think this is very important step for the future. Even in district heating grids, there's always the outlook now and trying to integrate some kind of sector coupling where we can balance between thermal and electrical grids. So it's definitely relevant on that part. But yeah, I think for now it's still very early phases with some of these technologies, and yeah, they definitely needs to see some reduction in costs over the next coming years to make feasible integration of all of them. But yeah.
Yeah, thanks.
I mean, for the French context also, this kind of building, which are quite efficient in terms of thermal insulation, because they were built not so long ago, not also connected to the district heating grid, are quite common, and they will be here for a long period. I mean, because lots of buildings are also getting renovated, or there is also new construction. So in that regard, basically we need to rely on any electric grid in France to decarbonate a bit the building sector. That's maybe not the case for other countries or Northern Europe country, where district heating and possibly with a large share of renewable energy in district heating grid are present, and that's why this kind of system bring a really good performance in terms of CO2 reduction. But in the end, integration of battery, of capacity storage need to be shortly thought, I would say, because they bring some additional capex also to the system, and they should be in the end paid by someone. So.
Thank you very much, Gilles. Are there more questions? No? So now the next presentation will be done by Clement, but I don't know, Clement, can we change with Alexander, because he has a limitation about the time. So we change this presentation. Okay, thank you, Clement. So so far the previous presentations focus on the all integrated system, and now for next presentations we will focus on some subsystems of this integrated system. So in that case, we start with a space heating subsystem. The presentation will be made by Alexandre Leblanc from Campa. So please, Alexandre, can you start your presentation?
Yes, good morning, everyone. Can you hear me well and see my screen?
Yes.
Yes, thank
the
you.
usual quick check. So, okay, nice to meet you. For the ones I don't know yet, I'm working in France for the company called Campa, and we are a manufacturer of heating systems, including electric heaters, heat pump, and domestic hot water cylinders. And we were involved in this project for the work package 3. So regarding the electric heater with PCM. So I will explain how the PCM is embedded and how it works. And also for a similar system, but which uses a heat pump to generate heat instead of the Effet Joule heating element. But regarding what has been demonstrated in Agen, so the demo site B, it's only the version with Effet Joule heating element, which is on the picture on the screen. So just a quick reminder of how it works. The purpose is to have in the room, so not in a technical room, but in the living room, for example, or the bedroom, the storage capacity, so that frees some space in the building and reduces the floor footprint of the storage systems. And it's an appliance that provides heat, so it interacts with the end user that can select its temperature setting for the room, set its schedule to say I'm here on the Monday, Tuesday, Wednesday from 9 a.m. to 9 p.m., for example. And on the other side, it's connected to the BEMS the BEMS says when the appliance should store heat. So quickly, what's inside? You see here some aluminum racks, which are set horizontally. These aluminum racks are filled with a phase change material, which is sugar-based. It's erythritol, which melts at 120 degrees. So at 120 degrees, when the core is heated up at this temperature, the phase change material melts and stores energy. And this energy can be used later. Typically, we are here storing energy for the intraday time period, and not over several days like some other storage systems. So we want to store in the morning or in the midday to consume the energy for the evening, or at worst, the morning next day. So as we commit for the SCORS project, we studied and optimized in details how the storage core works and how the heat is being stored in the phase change material, which is quite a challenge, as the phase change material, the PCM, is changing a lot of size when it's melting and solidifying again. So we had a nice work with IPS on this topic for mechanical and thermal simulations. And this led us to build the prototypes you see here. So 3 prototypes. So we built 5, and we installed, we commissioned only 3 in Agen. So just a few words about how the energy goes in and goes out. So you see, you take this picture. There are some heating cables that are inserted in the aluminum profiles. So the PCM is heated up with a heating cable all around the aluminum profiles. And to get the heat out of the appliance, we have an airflow circulation from the right to the left. The air is forced with the fan here. And when we want the energy to go out of the core, we force the air through the core to take the calories out of the aluminum racks. And when we want the energy to stay in the core, we just close the vents, stop the fan, and the heat is retained this way in the core. So the prototypes were tested in the lab to qualify their safety and performance. Yeah, it's not the topic for today, but just a quick look at the performance. So if we take this curve, which is a full charge and heat being maintained in the core. So we have here the integration of the energy being stored. In orange, the duty rate of the heating element, so which is representative of the heating power we apply to the heating cables, and the above curves are the core temperature. So you will see at 120 degrees the temperature step, which shows the phase change is initiated and in progress. And also the heating element management, which is done not to overheat the phase change material. So we go at a high power at the beginning, and then we reduce a bit the load of the heating element to avoid overheating. And a quick look at the discharge. So we can see that after 24 hours, starting from a fully charged core at a bit above 120 degrees, we still have, we have a full discharge of approximately 28 hours. So it's a maximum 1 day storage and not above. So if you come back to the demo site, so these pictures here were taken back in 2020. So it was in February 2020 when we finished the lab tests and prototype assembly. So they were conditioned and sent to Agen over a specific transport that you see here. Agen is not close to the place we are. So we are here in the north of France, and Agen is in the pretty southwest. So they traveled a lot. You see here the picture of the demo site B. So commissioning took place, as I said, in February 2020. So we were a small team of the SCORS project to gather ourselves and install various subsystems at the same period. So on the pictures on the left, you can see Pierrick from EDF, which is still installing cables for communication. The team from Siemens from the Netherlands, and here the team from Heliopac. So commissioning, it was on one side easy, and on another side quite difficult. Easy because the appliance is very easy to install. It's just a 3-wire connection to the electrical network to bring power supply. And it was also quite complicated as the battery cabinet in which the BEMS is installed is at the exact opposite of the building. And to secure the way information was communicating between the apartment 6, in which the electric heater are installed, and the BEMS is located, we wanted to have a direct Ethernet cable So the blue wires you see here are direct Ethernet cables that goes all through the building to link the EHPs to the BEMS. So yeah, we had quite trouble with these Ethernet cables. Yeah, within 2 days, the system was up and running, and the BEMS communication was operational. So here you see the 3 appliances being installed. So in the living room and in the 2 bedrooms. Unfortunately, in March 2020, France was, as many countries over the world, hit by the COVID, so the lockdown was declared. So not all the systems of the SCORES project could take place in the building, but yeah, ever since for the EHP, so since February 2020, they were heating the room, consuming energy. The interaction with the BEMS was technically okay, but as the BEMS did not send orders to charge, discharge, the appliances were not used at their full potential. And to my knowledge, the flat, which is called the apartment number 6, was not occupied during the demo in Agen. So during the 2 years of demonstration, the data and the telemetry of the appliance, so meaning the duty rate of the heating elements, the energy being stored, the room temperature were recorded by the BEMS, and the data is collected by the team of EDF for analysis. So it is part of the deliverable of the project. And 2 weeks ago, the 3 appliances were decommissioned because the owner of the apartment wanted to get the space back, and so we got the appliance back here in the north of France, and the heating system of before, which is heat pump based, was put back in operation. So here's the summary of what was set up, commissioned, and demonstrated in the demo site B regarding the EHPs, so the electric heaters with PCM. Yeah, if you have any questions, don't hesitate to ask.
Thank you, Alessandro. Are there questions? Okay, but I have one question, Alessandro. Is Campa thinking to put this equipment in the market in a near future?
For the next heating season, which will start in September 2022, no. But for further heating seasons, we are reusing part of the technology which was demonstrated here, and thinking of a product that embeds it. Yes, but the economic viability of such an appliance, because it's more expensive to have an appliance that stores energy compared to an appliance that doesn't store energy, because it requires more material, more electronics. So to justify this overcost, the end user must have a payback, and the payback is generally given by self-consumption or peak shaving services, or demand-side management services. And today, these services are not at the end user's level, not paid back directly on his electricity bill, or at least not sufficiently high to justify to have so much storage in an electric appliance. So we are also waiting for, in a way, paradoxically, the rise of the energy prices will help such systems to appear on the market and to find their economic viability. I am not wishing the energy prices goes up. We are only wishing that the energy prices vary more over the day, over the seasons, to give the room to more to systems that will enable to use better energy.
Yeah, and we need also to have cheaper PCMs in the market at the same time.
It's another way to to spread the technologies to a lower cost.
Yeah, thanks. Are there more questions? No? Okay, thank you very much, Alessandro. Thanks. And now we pass to other subsystem. So we will present now the domestic water production system based on water-to-water heat pump coupled with the PVT or PVT collectors in the demo site. The presentation will be made by Clément Dumont. Clément Dumont is mechanical engineer working for Heliopac for needs of SCORS project. So please, Clément.
Yes, hello everybody. Can you see my screen and hear me well?
Can you put in a presentation mode, Clément? That can help to see better.
I don't know how to do it. This way, is it good?
You can try to press F5.
This way?
No.
Play on your second screen? No? You have two screens?
I don't have two screens right now.
Or just share the window and not your full screen?
Yes, this is what I do. But maybe if I share the full screen, we can... Up. This way.
Yes.
Okay, yes, that's it. Fine.
That's better.
So I'm Clément Dumont. I'm working for Heliopac, and I will speak about our technologies and what technologies we installed on the demo site. So the company, Heliopac, is a French company. We design and manufacture collective domestic hot water production systems based on heat pumps, and we use the sun as a heat source. And we provide support for our systems and commitments. We have 30 years of experience in the field of renewable energy and the production of domestic hot water. In France, we have already installed 800 installations and 55,000 square meters of collectors in Europe. Our domestic hot water production solutions are divided into two categories. We have water heat pumps and air water solutions. And so we have the simplest, the more simple system is the Heliopac system. It's basically a solar collector placed on the roof most of the time, and the solar collector collects heat and as a heat source for the heat pump. Then we have the Heliopac System Plus, which are the PVT solutions that was presented by Erwin in the first presentation. It's photovoltaic panels coupled with solar collector, so it can provide heat and electricity. And then we have some Geopac system that use the geothermy as a heat source. So the Heliopac system is a solutions that use a low temperature flexible solar collector. And the solar collectors can be used in almost all climatic conditions. Actually, sun, rain, wind, and fog are elements that favorize the recovery of renewable energy by the system because they are convective collectors. Here we can see some flexible collectors of this Heliopac system. There is more photos here. So it's a convective temperature collector, and it collects the heat from the ambient air at a huge rate of 80%. That's why even if it's not sunny, the solar collector keep produce heat. The solar collector are flexible. They have a low wind resistance. They are light, and the material used is the EPDM that have at least 30-year lifespan because Heliopac is only 30 years of life. And yes, we are still looking at the lifespan. Yes, so more points here. As it's a convective, it can work also into the night. There is low maintenance on the roof. There is no risk of overheating the solar circuit. The collector expands, so there is no need to install an expansion vessel to counteract overpressure. And yes, it saves space on the roof. Now we have also Heliopac System Plus. It's photovoltaic panels with solar with heat collectors behind the panels. These panels are manufactured by a French company, Dualsun. So, I'm sorry. You can see on the photo that there is a electric grid and also thermic wires that represent the solar part. So with the Heliopac System Plus, a very large part of the energy needed to produce the domestic hot water can be provided by the system if we take into account the renewable heat and the electricity. So it's a very low CO2 emissions system. The cooling of the photovoltaic cells by the heat pumps improves their efficiency from 10% to 15%. The operation is mostly continuous because it's convective. Yes, and it's low maintenance, like a normal photovoltaic system. It's factory assembled and easy to install, and it saves space on the roof. Now I will speak about the demo site B in Agen. In this site, so you can see the red point in the front. This is Agen, and in Agen we installed an Heliopac System Plus. Here is the building. Yes, already know that. Yeah, so 130 PVT panels. We have 7 cube meter of water buffers and 3 heat pumps of 12 kilowatt each. And on one roof, we installed the PVT, the panels. So that's it for the demo site B in Agen. And at Heliopac, we also have a remote control system named Heliopad, and it means that every installation is connected through internet, and we can manage the system by an interface like this. So here is the schema of the Agent installation. We have the 3 heat pumps in yellow on the left, and the three water tanks. And we can see also the PVT panels and the primary circuit in black that provides the heat to the heat pumps. So with the Heliopad system, we have the tracking site, and we can look over every site in France to follow the consumption of the systems and the energy produced. So here is the map for the demo site in Gleisdorf, in Austria. And the system installed in Austria is close to a Geopack system, even if it's a specific configuration, because the district heating acts as a geothermal source, but it's a district heating. Yes, the district heating provide the heat as a primary source of energy, but there is also another solar thermal circuit in Gleisdorf that can complete the heat production as on the primary circuit. Sorry. Heliopad is present at the international. For example, Heliopad equips 2 buildings elected at the Green Building and City Solutions Award during the COP22 in Marrakesh. We also equipped an eco-quartier at Fort-d'Issy of 1,600 dwellings and 2,300 square meters of shops and office. So yes, that highlights the fact that we mostly install our system in the collective configurations. Yes, and there is also a lycée of 80-bed boarding school and 8 staff houses. That's all from me. Thank you for your attention. Yes.
Thank you very much, Coleman. Are there questions to Coleman? Coleman, I have one question. If you have many days in row without sun, the panels have the capacity in terms of heat transfer to provide heat to the heat pump to produce all domestic hot water that we need?
Yes, there is actually also backup heaters, backup electric heaters inside the water plants that we use in that case.
Mm-hmm.
But yes, actually we dimension the systems to prevent this kind of situations to happen to many times in a year.
Yeah. So in that case, of course, this system is more efficient for the regions who have warmer climatic conditions than in terms of regions in north of Europe where the outdoor air is very low during the winter and without many hours with the sun. Okay.
Yes, of course.
Yeah. I find. Are there more questions? No? So in that case, we can pass to the next presentation. The next presentation is about the building energy management system in the demo sites. Will be presented by Hans from Siemens. Hans is not available to join us today, but he recorded a video to show his presentation. So I will share the video. Okay, can you see the video?
Yes.
And I suppose that we will also to hear the sound.
Hello and welcome
Yes.
everyone.
Fine.
First of all, apologies. I couldn't do this presentation live because I had prior arrangements. So I've recorded this to see for you what we've done in this project and why we've done this. My name is Hans Hennig. I'm an HVAC consultant for Siemens, and together with a couple of colleagues, I've been working on the BEMS of this system. And the BEMS is the Building Energy Management System. And there's a large difference between the Building Energy Management System and the Building Management System. One takes energy into account, the other one doesn't. Normal building management systems, they take into account the demands of the user and try to keep, for example, temperatures at certain levels, and they don't take into account anything like solar energy or energy that's available from wind or another source. It simply assumes it's there and it starts the process at the time the requirement is done and not when it's optimal to start it. You see slow change in that. Some systems take, for example, solar loads or shading into account in their calculations and in the way they control the equipment, but that's only beginning to start. Certainly not mainstream. As you've been told, we have two demo sets up, one in Agen and one in Gleisdorf. In Agen, you have this field equipment shown at the bottom here, and you have generation equipment in the form of, for example, solar thermal panels that give electricity as well as thermal energy. Both, of course, are connected, and on top we've placed the BEMS as a kind of a brain. The BEMS takes in user profiles and user data and forms a profile based on that. And it takes in energy prices and capacity prices, but also weather predictions and other stuff. And based on that, it determines a strategy. That strategy is communicated to the field equipment below, and then the field equipment executes the energy strategy that the BEMS devised. We have something similar in Austria. Austria, the main difference is that you have a district heating system that provides an alternative source of energy as opposed to electricity, and that the two are kind of independent. And next question is, why is it so complex to do something with energy? Because the simple answer is everything is interconnected. And I'll give you an example. For example, if you want heat, you can get that from a couple of sources. In Austria, you can get the district heating or a heat pump or a buffer or something else. But if you take district heating, you have to take into account the temperature of the district heating grid. That's not constant. If you take the heat pump that uses electricity, then the energy will come from either PV or the grid or the battery. That means if you use it, others will have less at a certain point in time. Or it can come from the buffer, but that means you have to replenish the buffer, otherwise it will go empty, and that's something you do not want. And you can do the replenishing by a heat pump or district heating or the CLC, but that means you use the CLC in this case, and once the CLC starts running, you can't simply stop it because it will run for at least 2 hours consecutive, and if it discharges, even more. So that requires planning, and you can see where this is going. This is becoming quite complex, quite fast. We had an algorithm set up based on two algorithms that are running in parallel. And the optimal solution, and optimal in this case means self-consumption or cost, is set up by in this way. We had a modular approach, and the modules are programmed in JavaScript. The algorithms are, one is the prediction algorithm and one is the decision algorithm. Decision algorithm makes predictions based on, let's say, independent variables, and it uses lots of regression and some statistical formula, physical formula for that, and it determines how much energy you have as a net result of all the things you've done. So the surplus, and then you have the decision algorithm that decides what to do with it and how to do it well. And the prediction algorithm, what it tries to do is predict the PV surplus in the case of Austria. And of course, it in an oversimplified form, it'll look something like this. You have the red areas here where energy is consumed, and the blue area where energy is produced. And if it's winter, then the produced area will be less because there will be less sunshine. But in the summer, you'll have more solar energy, so you can distribute more. And now the prediction algorithm will determine the shape of this curve, and the job of the decision algorithm is to distribute this blue area as wisely as possible over the red area. And wise, as I said, can mean economically, but can also mean self-consumption wise. This is theory. In practice, the shape will look more like this. This is a part of a simulation, but the reality will look like something similar. Some background data on the prediction algorithm. It runs every hour because of the input every hour. The decision algorithm will run more frequently because it will take into account the status of charge of, for example, buffers, and things do change within the course of an hour. So that's why it runs more frequently. This is an example of the BEMS we did in, I think, Austria. What you see here is you see the server on top where the algorithms are running, where the logging is done, where the storage of the data is done, and where the APIs come in. And of course the switch below it, because all the network components need to be connected. Then you need a controller to do the actual controlling of the subsystems. They don't understand most of the controls, so you need some kind of interface to them. Parked below, you need an internet connection, and you need, of course, the power supplies to get this all running. On this hardware, we also run the user interface, and it will look something like this. And this is a picture of the CLC. It can override the decisions the algorithm has made, and it will give you, let's say, an up-to-date picture of a certain piece of equipment, in this case the CLC. Something similar, for example, for the domestic hot water. And you can see, for example, here that there are also errors occurring, and the algorithm has to decide how to deal with the errors. And things that are on here are temperatures, pressures, things like that. This is something else. This is a printout of the log file, and apparently there was a test in the system that required 2 consecutive charges of the CLC. You can see them here. So you see the number of reactors being charged going up from 0 to 2, and later on there's a discharge action, and the reactor goes down again. And then during charging as well as discharging, energy is released. So you see 2 times increase of energy in the CLC buffer. And because the discharging especially requires the buffer temperature inside the CLC to be below 42 degrees, we had to dump energy from the CLC buffer into the scores buffer before the system could get started. During our test runs, we had a kind of an unexpected opportunity. On the 15th of November, the system in the district heating in Austria broke down, and it had completely cooled down during the weekend. And you can see that here, the temperatures 20 degrees, you cannot do any heating with that. And the Monday morning after, I got a call at 9 o'clock from Wim, can you do something? So we switched on the system, and the system immediately started to deliver heat to the building, and as a result, the building rose in temperature and people were more comfortable, because when they come in, it was cold. Up until midday, the system kind of stabilized, and the building was up to temperature. It's a low temperature system, so floor heating and other low temperature equipment. So 50 degrees, as you can see here, is more than enough to do the heating and the cooling. As I said, by midday, the system was up and was on temperature. Temperatures remained quite high, so there was energy in the buffer. And at about 3 o'clock, the existing system, so the district heating system, was repaired and was brought back online again. And you see a power increase here, because then the district heating system started to heat up the buffer of the score system. Intentional, but that means an increase in power. Yeah. And this brings me to a point why renewables are so important and how to deal with them. Because if you look at the situation, for example, in Russia, with all kinds of prices skyrocketing, then you need more renewable energy. And renewable energy means more planning, and more planning needs a BEMS. And for BEMS to be rolled out over a large population of systems means you have to get away from all kinds of handwork, because that takes time. So you need to go away from the physical models, and you need to go into AI. In addition, you need a preferably small number of languages with no dialects, because they take time too, because things are the same but slightly different, and that it takes always time in the process to figure out what exactly is it that the system means. Horrible if you have to do it on a large scale. What you should what should remain is the modularity, because then you can work on some systems while others simply remain in operation, and you can replace things fairly easy. But large system rollout of the BEMS also means that it has consequences for the systems that are in place in the various buildings, because they need to be controllable. And if you don't have any actuators in a building, you can't control it. So that means the building management system of each building has to make a shift from a demand-based, your user-based system, to a more supply-based system. That means, for example, the BMS has to calculate how long it can postpone certain processes before they become critical and the user experience gets damaged or gets adversely influenced. So that's something coming from that system. Also, the number of equipment in the building that can store energy must increase. For example, if you have a system with no buffers, you can't store any heat or electricity or something else. So that those systems need to be in place and installed. And of course, for heating, you'll have the thermal buffers. And as Pavel will tell you, you can do that efficiently without hardly any losses. And the same is true for the electricity in the form of batteries. And what you will also see, I think, in the near future, is that certain functionality of the BEMS will be already incorporated into the standard building management systems. For example, things like peak shaving, you already see first developments, at least in our system, that there are limited things to reduce the peak loads in the system, and that will increase even more. And of course, commands from the BAMs need to be translated so that the building management system understands them and also sends information back to the BAMs, like this is what we can do, and this is not possible, so use energy from the grid or find another solution. That's my outlook for the future. I would say this is, for now, everything I wanted to share with you. If you have any questions, either contact me or contact Louise. I'll be happy to answer them. I'll work on it to answer them as quickly as possible. Thank you very much for your attention, and I hope to see you soon. Bye.
Okay, so Hans is not here, so anyway, if you have questions, you can send an email. We will share also these presentations. I forgot to introduce Hans. Hans Henning started 4 years ago with Siemens. Before that, always as an heating, ventilation, and air conditioning consultant for various companies in advisory, construction, energy. He's a mechanical engineer with a Master of Science in Business Administration by training, with an interest in programming. A professional goal is to line up technical solutions, the environment and money, for focusing on total cost of ownership. As this system is a very complex system, so we have different energy production, energy sources, so we can receive energy from the grids with the different tariffs along the day or during the week. We can also to receive district heating heat with the different tariffs. We can have also the different radiation, solar radiation levels in every day. At the same time, the consumption profiles can be different along the day, along the week. So we have weekdays, we have weekend days, and so the profile can change too much. At the same time, too difficult more the system, we have in the middle the energy storage, and we have the different types of energy storage, so electric batteries, CLC, PCM. So we need a very strong, smart and self-learning building energy management system to get most out of this integrated system. Otherwise, we cannot use the potentialities of this system. So the building energy management system is very, very important for the future systems based in the different renewable sources, in the different prices of the grids, and also using different kinds of energy storage. So now we passed for the next presentation. So the next presentation is about highly efficient isolations based on GVI technology applied to thermal energy storage.
Welcome to the training series.
Can you see the video and now?
Yes, yes.
Yeah, okay.
Series of the SCORES project, where partners introduce the concept, technologies, and their demonstration. In this video, Fabian Schansker from Koenig Metal will talk about heat battery based on GVI insulated water vessel. What is the working principle of the GVI technology for supported vacuum insulation?
GVI is a vacuum insulation with a stainless steel envelope whose gap is not simply an evacuated space, but completely filled with a microporous supporting material.
How does GVI contribute to increasing the energy efficiency of the heat battery?
For storing heat, whether in sensible or latent form, an effective insulation is crucial to achieve an efficient storing system. Better insulations enable higher storing temperatures, but particularly longer storing periods, which is necessary to handle the volatility of renewable energy sources.
What are the advantages of GVI technology compared to other thermal insulation solutions?
GVI combines a set of properties which in combination are ideal for many applications. The thermal conductivity is lower compared to unevacuated insulations like foams or fibers. The mechanical strength is unmatched due to the sandwich structure, which consists of two thin stainless steel layers that are pressed against the core. This leads to a very stiff laminate while being lightweight. This is in contrast to dual or multi-layer insulations. Moreover, the latter ones are restricted to rotationally symmetric bodies, while GVI products can have any shape you desire. Last but not least, the material is resistant against most chemicals, as well as high temperatures up to 450 degrees centigrade or even higher if needed.
How mature is the GVI technology developed?
We have proven the GVI technology in various prototypes, in the lab as well as in the field under real-life conditions. Our next step is to bring the first products into a series production.
Can this technology easily replace other thermal insulation solutions in other applications, namely in cooling, heating, and hot water systems?
Yes. As mentioned previously, our insulation can take any shape, including openings or feed-throughs, and thus easily replace existing insulation solutions. But this means you can either increase the efficiency of the existing storage or increase the usable space by making the insulation thinner.
SCORS gathers 12 partners from 7 European countries who are working towards the common goal.
Okay, so nobody's here to reply to your questions. Anyway, I think it's a very interesting result of this project. Based in this technology, it was created a spin-off to commercialize this solution. It's a very efficient solution for thermal insulation and can be applied to different thermal energy storage systems like hot water, PCM, CLC, as we presented before. So if we are using high temperature thermal storage, of course, this can produce a very efficient way to isolate these kind of solutions based in high temperature. So it is a very, very interesting result of the project. Anyway, if you have some questions about this solution, you can send me an email and I can pass to the colleagues that developed this solution. Okay, so this is the last presentation. We are close to the end of the seminar. I don't know if you have some questions, comments. No? So you can use the web page of the SCORS project, mainly the training series, a page about the training series. There are many materials about for training on these technologies. And and if you have some comments or questions, you can send us your questions. So thank you very much for attending this seminar. Thank you very much for the presenters, for your collaboration, and see you next time.
Okay, thank you, Luis. Have a nice day.
Thank you, Luis.
Thank you very
Bye.
much. All present. Bye-bye.
Bye.
Thank you.
Bye.